Hi everyone, in this video we are going to discuss nitrous oxide. So nitrous oxide, also known as laughing gas, is typically used as a local anesthetic. The problem is nitrous oxide is one of our biggest offenders when it comes to greenhouse gases. So let's review a couple facts about this. The molecular formula of nitrous oxide is N2O. So now, in the year 1750, we had a concentration of around 275 parts per billion of nitrous oxide in our atmosphere. Now, currently, in the year 2015, we have around 350 parts per billion of nitrous oxide in our atmosphere. So we haven't increased too much, especially in comparison to the other molecules we've been discussing, but we have increased a little bit. The big problem with nitrous oxide is that it has an incredibly long lifetime in our atmosphere. It is around 120 years. So this long lifetime plus its small concentration gives it a global warming potential of 310. So it's really, really high. So it's much higher than methane and much, much higher than carbon dioxide. So before we move forward and talk about our sources of nitrous oxide, I want to review a couple questions about its molecular geometry. So I'm going to draw out a couple structures here. So there's this one. And so let me draw in my lone pairs here to keep everyone on the same page. And then I have another structure over here. So we'll just draw it out like this. And I'm going to give this one 2 lone pairs as well. Okay, so now what I want you to do is complete the following sentence here. There are 2 equivalent blank, I'm looking for a specific word, structures of nitrous oxide, of N2O. Go. Did you get an answer? Hopefully you did. The correct answer is resonance. Resonance structures. So anytime you see this arrow right here, we are trying to tell you that there are resonance structures. So there are equivalent structures or 2 correct ways to draw out this molecule. All right, next question. Of these molecules, what is the molecular geometry? Go. Did you get an answer? Hopefully you did. The correct answer is linear. There is no other way to draw this out except for in a linear geometry. Next question. What are the bond angles? Go. Did you get an answer? Hopefully you did, and all you had to do was look up here at the structure and determine the angle right here, and that angle is definitely 180 degrees. Anytime you have a linear molecule like that, we are definitely going to have bond angles of 180 degrees. Now, moving forward, what are our natural and human sources, or our anthropogenic sources of nitrous oxide released into our atmosphere? So let's look at the natural sources first. There are 3 main ones that we talk about. The first one is just regular old soil. So essentially what happens is you have soil and the bacteria comes in and interacts with the soil and the organic compound there, and we essentially release our nitrate into the atmosphere. However, this nitrate is then eventually broken down through many, many steps into 4 different, well, mainly 4 different nitrogen-containing compounds. So they create nitrogen by itself, they create nitric oxide, they also create the nitrite ion, NO2 ion, but the most important one for us is they create our N2O, which is what we're talking about. So anytime we have soil and any form of bacteria that interacts with that, we have this whole nitrogen cycle, but essentially we are constantly releasing nitrous oxide into our atmosphere. Now, the second one we look at is up in our stratosphere, or anytime when we have UV interaction. So we have these very stable molecules of nitrogen and oxygen, but when they're in the presence of very high energy radiation, so UV radiation, they can actually force these molecules to decompose and come together and create N2O. The last natural source that we're going to talk about here has to do with ocean upwelling. And if you're not familiar with this term, essentially what it is in your ocean, you have this deep cold water that is brought up to the surface of the ocean. But when it does that, it brings the minerals and it brings the things, the components from the bottom of the ocean floor all the way up into the ceiling or to the surface. And then we release N2O into our atmosphere. So we're just releasing nitrous oxide there. All right, now what we want to do is talk about our human sources. So what do we do that actually create and then release nitrous oxide into our environment? Well, one of the most common ones, and we've talked about this before, are catalytic converters. So catalytic converters are amazing and they're super, super good for us because they take carbon monoxide and they convert it to carbon dioxide, which is good because carbon monoxide will kill us, but carbon dioxide is heating the planet. The problem is it also takes these NOx compounds and converts them to N2O, which again, it's better for air pollution, but it's not good for global warming. So there's good parts and bad parts of these catalytic converters. All right, the next one we want to talk about are any form of ammonia, I don't even know what I wrote there. Let's try that again. It's ammonia fertilizers. Now, ammonia fertilizers, it's the exact same chemistry as we discussed above. We have the soil, we have the bacteria, it breaks it into our nitrate ion, which then breaks it apart into all those different nitrogen-containing compounds, but specifically for us, the nitrous oxide. Now, there's two more we talk about. One of them is when we burn biomass. So essentially when we burn our crops, and what we do is we just are now releasing our N2O into the atmosphere because we have incomplete combustion. So the incomplete combustion forces N2O as a byproduct, and so we release it into the atmosphere. Last one we talk about, which is one of my favorite ones, is industry. And so in a lot of industrial processes, we are creating N2O as a byproduct. One of them is nitric acid, and another one is nylon, which is interesting. The chemistry is so cool when it comes to nylon, but we are creating N2O as a byproduct and releasing it into the atmosphere. So let's go through this and see if we understand kind of one question here. So right now, our global warming potential has three different categories when it comes to nitrous oxide. So we have a 20-year rating, we have a 100-year rating, and we also have a 500-year rating. So our 100-year rating is the one we've been reporting to you, which is 310. The 20-year rating is actually 289, and the 500-year rating is 156. So my question is this: why? Why do we have such a decline in the global warming potential? And what's up with the year? What's up with the number difference? What's going on here? Please explain that to me. Did we come up with an answer? Hopefully we did, and essentially it comes down to two main components. The first one, and the most important one, is that we have a lifetime, or nitrous oxide has a lifetime of 120 years. So if we stopped today and stopped all forms of human sources of nitrous oxide production, our environment would still have 120 years to get rid of all of the nitrous oxide that's up there. However, regardless of this, we still have natural causes. So we're never, ever going to be able to just stop our nitrous oxide on the planet. We have these beautiful nitrogen cycles that create this N2O and are constantly putting N2O into our environment, which is going to happen. We need it to happen in order for us to survive. So this GWP value is never going to become zero. It's always going to exist, but we can cut down our human sources and make that number as low as possible. Good luck, guys. Take care of yourselves and have a fantastic week.